Good morning, everyone. Welcome. I'm going to just take a little bit of a slow start while everybody joins on. I know there's quite a few people yet who we expect to have join. But in the meantime, welcome. My name is David Chassin. I manage the Grid Integration Systems and Mobility Group at SLAC National Accelerator Laboratory. For those of you who don't know, SLAC is a DOE national laboratory. It's operated by Stanford University. And we conduct a wide variety of work for the U.S. Department of Energy and for others, including the California Energy Commission, which is the agency that is funding this particular work. And so I want to particularly recognize and thank the commission for their support. And especially recognize and thank Cheng Tian and Alan Lee, who I believe will be joining or have joined already, for their support and assistance in getting all of this work done. So before I go much further, I just want to highlight the fact that this is developer training. And so it's focused on, what I think we would colloquially call power users of Gridlab-d. So this is going to be training that is designed for people who really want to get into the nitty-gritty details of how the simulator works. Because we have two other projects for the California Energy Commission that are sort of designed at more conventional users, there will be training sessions for those as well. But this one is focused especially on the simulation engine itself. The Gridlab-d Open Workspace, or GLOW, which is work that is conducted by Hitachi, led by Bo Yang, also for the California Energy Commission. That project is focused on a user interface, and we will be holding training sessions for that. Well, Hitachi will be holding training sessions for that at some point in the future. We also have another tool that we're developing for the commission called Open FIDO, the open framework for, see if I can remember exactly what it is. Right, I'm sorry, right off the top of my head, I don't remember what the acronym stands for. My bad. But that's basically a data interchange framework for tools that include Gridlab-d, but other tools that utilities use. And there will be also separate training sessions for that. So as I said, this is focused primarily on sort of what you would think of as the power users of Gridlab-d. And so we will spend the next 12 or so sessions, each about 2 hours, talking about Gridlab-d, how it works, and the work that has been done over the last 4 or 5 years under CEC funding to commercialize and make the tool more readily accessible to users more broadly. So what I'd like to do is, so let me first check, did everyone see the screen change? Everything's working okay? I'm assuming everything's all right. If anyone is having problems, let me know, but I'm seeing some thumbs up, so I will take that as a affirmative. So over the next, well, what we've planned is 12 weeks, but what I'd like to also ask you is if you have ideas for other topics that you'd like me to cover that would not likely be covered by the GLOW or Open FIDO sessions, let me know in the chat. And I'm happy to add those topics on. We can run, 13, 14, as many sessions as is necessary to meet these needs. We will be holding the sessions regularly on Monday mornings to the extent that holidays and my availability permit. If we have to skip a particular one, that's okay. We can run into the fall without any difficulty. The current schedule is that these will begin, originally we intended to begin in the first week of June. Obviously we delayed a little bit, but these will run through the end of August. And if necessary, we'll run into September. It's not going to be a problem from a scheduling standpoint for us, and hopefully won't be for any of you. So as I said, please feel free to suggest other topics that we might cover. But what we're going to cover today is an introduction to Gridlab-d and just kind of a high-level overview of what the tool does. Next week, we'll focus on building Gridlab-d. Obviously, to most users, building the tool is not something that you generally want to have to do. But for power users, it's not uncommon to want to build it from scratch so that you can enable features and so on that would not normally be available. The third week, we'll talk about general modeling topics related to Gridlab-d and the modeling language itself, and how we represent systems in a simulation environment like Gridlab-d. The fourth week, we'll talk about testing and validation of Gridlab-d models. For those of you who are familiar with the tool already to some extent, you know that that is a rather challenging problem, and it's one that we've spent a lot of time trying to address, and we have a variety of interesting topics that we can talk about there. And then we'll get into sort of the details of how the tool works, talk about modules and classes that are used to create objects in a simulation. We'll talk about how the following week about how the core engines work and how the solvers work. And then we'll talk about using Python to create libraries and extensions. We'll talk about the data and model converters that allow us to move data in and out of Gridlab-d to other tools. We'll talk about geodata packages, which is a significant extension that we introduced that allows us to do a lot of geographic data processing. And as you know, a lot of the use cases that are emerging these days for utilities do involve this kind of geographic information. And it's something that we'll spend some time looking at understanding how that works and how packages can be created or linked to Gridlab-d. And then we'll wrap it up in the last 3 weeks with discussion of some of the ways of extending Gridlab-d using subcommands and adding tools and utilities. And then finally, the production and release system that exists today and will probably be updated as we commercialize the tool. So that's just a high-level overview of what this summer's sessions will do. As I said, if you have any suggestions for other topics, I'm happy to add them on. You know, to the extent that I can answer the questions that you are interested in learning more about, we'll try to align those as best we can. So with that, I think I'm ready to jump in unless you have general questions. I will probably proceed. So, and by the way, if I miss somebody raising their hand, just go ahead and interrupt me. That's fine. It's best to answer a question when it comes up, and there's plenty of time to do that. Don't, you know, just feel free to interject if there's something that you want to particularly get answered at that moment in time. So let me start with just a broad history of the tool. The development of Gridlab-d actually goes back about 20 years. The national laboratories have a program that they've been running for many, many years called the Laboratory Directed Research and Development, commonly called LDRD. It's funding that the laboratories basically source internally to develop sort of high-risk, high-reward potential ideas. And about 20 years ago, a colleague of mine at PNNL, Ross Guttrimson, and I proposed to develop a new kind of simulation tool based on an idea that had come from the economics side called agent-based simulation. And we felt that this was an interesting approach to solving a problem that had existed in sort of the energy sector, energy research area, between the folks who model buildings and the folks who model power systems. And the reason that it was a challenge was that these two systems behave on different timescales and often didn't really present problems in the same manner. So in the building side, we tend to think of sort of hourly energy consumption as the primary concern. And a lot of the building simulators at the time, the vast majority of them, in fact, focused on sort of hourly energy simulations spanning a year with typical meteorological weather data to try to understand, for example, how a change in the building energy code would impact energy consumption. Meanwhile, over on the power systems side, the power system simulators tended at the time especially to focus on solving sort of a situation, right? You look at a condition, for example, a scenario on the power grid, and you might study the dynamic transient response of a system to a fault, or you might study the steady state power flow solution under a particular range of scenarios so that you could optimize, for example, power flow or some such thing. But generally, connecting a building's behavior to the power grid was something that was not easy to do. Because if you think about each of these simulations, the things that they care about at the boundary were regarded generally as static. So the building would regard the voltage as static and the frequency. And the power systems simulation would regard the building itself as potentially static, either time invariant or voltage invariant. And so connecting these two together was very challenging. And so this LDRD project addressed that larger question of how do we bring these two kinds of models together and produce a simulation where we can explore how the building's behavior can be helpful to the grid's behavior, and how grid information can be used to enhance the performance of buildings, particularly cost performance, but also potentially controls and such. And so this was a challenging problem, and the simulator that came out of this was a proof of concept that was demonstrated, and several really interesting papers came out of it, and it led to DOE's commitment to invest in a new kind of simulation environment, and that became what was called ultimately Gridlab-d. And the purpose was to really start to study smart grid technologies. How, this was at a time when there was a general realization in industry and at DOE that things needed to change, or that the power grid might not be able to keep up with emerging technologies. And so it was really useful to have a tool that allowed us to examine some of the potential directions we thought the grid might go. So the development of the tool led to some really interesting early studies that DOE funded. And many of these are highly cited papers, work that was quite influential in thinking about the direction that smart grid technology would go. And so there was a lot of really interesting work that was done at PNNL and NREL and other places based on this simulator. So one of the things that came out of it, is something that I'll talk about further today, is a taxonomy of feeders in North America that exemplify sort of the variety of network systems and designs that you find in North American distribution feeders. And these feeders became a very important part of the work that was done subsequently, because they're used to extrapolate information that you would get from a single simulation or a single study in a particular location to the rest of the nation. And that was used in particular in an early study that examined conservation voltage reduction. And I'll talk about that a little bit more today as well. But it's also used to study a number of other things like transactive energy systems, which some of you may be familiar with. The idea that we could use price signals at the distribution level as a kind of control signal for dispatching distributed energy resources. So since that early work, PNL has done a lot of additional work And some of that work has not been included in HiPAS simply because it's kind of hard to keep up with everything that's going on. There's so much being added to the research version of Gridlab-d, but there will be some effort in coming years to transition both changes that have been made in the commercializable version, the CEC version of Gridlab-d, back to PNNL, and of course moving recent additions from PNNL into the commercialized version, particularly the transient dynamic solver and the ability to switch back and forth between transient and steady state solution or quasi steady state solutions. And of course, the Helix co-simulation support in Gridlab-d that allows Gridlab-d to run with other kinds of simulation engines, in particular transmission system solvers and so on. So this kind of gives you a broad history of the tool and some of the work that led to what we've been doing recently with support from the California Energy Commission. All right, so let me spend a moment talking about why the California Energy Commission originally had us develop a version of Gridlab-d that was commercializable. Obviously, the CEC had some very specific objectives that it wanted to achieve. And so those were set out at the outset. Some of them have changed a little bit over time in response to evolving conditions. It's been 5 years since we proposed this work, and some things have changed, not greatly, but enough that there were some slight changes in the direction of the project. And the technical advisory committee that's been immensely supportive and very helpful to us in the direction that we've gone. We are very thankful for the support that we get from the technical advisory committee. They've also helped us, make course corrections along the way. But at the outset, the main goals have basically stuck. One was to improve the performance of Gridlab-d generally for the kinds of problems that utilities would typically encounter. Gridlab-d's original design sort of objectives were for a research tool. And so its performance was really oriented towards the kinds of problems that DOE was seeking to address. And it was not necessarily well suited to the kinds of problems that utilities might need to address. And so some adjustments have been made in HiPAS to try to sort of reorient the tool to better support utilities. Also, obviously with the development of GLOW, there's a high interest in making the tool a little bit more usable for non-experts. And so there's been some significant changes to the way Gridlab-d ingests data and produces data to make it a little bit easier for non-experts to use the tool, even if they're choosing to not use the user interface, so that the gap between the system that is presented at a sort of a user interface level and the system that you use when you run at the command line is bridged a little bit better. And so we'll talk a lot about those kinds of things. In addition, there's been a lot of changes that have been made to improve support for developers. So running on more platforms, supporting modern CI/CD, things like Circle CI and GitHub, and Docker and AWS platforms for enabling broader delivery and support of a range of users. There was a keen interest in using machine learning and artificial intelligence and big data. And so there's been an effort to include tools which take advantage of these technologies. And of course, address all the emerging use cases in California. And so we'll go over those in a bit. And then finally, to support the GLOW and the Open FIDO projects directly and make sure that everything that's developed in Gridlab-d directly enables capabilities that are necessary for those tools. And then we've obviously been very focused on the commercialization aspects of this. and making sure that we support the major utilities in California, and support the workforce needs that are emerging from the transition from sort of a conventional grid to the modern 21st century grid. So I mentioned there were some use cases that we were originally set out to develop for Gridlab-d, and that with input from the Technical Advisory Committee, we kind of revised and changed. So originally we proposed to support integration capacity analysis, which is the problem of understanding where we can add solar to the system, and locational net benefit analysis, which is the problem of understanding where distributed resources offer the best advantage to utilities and their customers. With input from the Technical Advisory Committee, it was deemed that the locational net benefit analysis had largely been satisfactorily answered by the utilities already, and we didn't need to do further work in that area. And so we added 3 new use cases that emerged over the last 4 or 5 years. The resilience problem, which is sort of a large looming issue, particularly with climate change stresses on the system. Electrification, which is essentially to address the decarbonization of the grid. And tariff design, which is really meant to address the impact of the other use cases on rates and revenues. And then we made a slight change. It's almost, I guess, a definitional change. Rather than thinking about integration capacity analysis, we're calling it more generally hosting capacity analysis, and not focusing just on solar, but also including batteries and EV charging, transportation infrastructure capacity analysis in the overall methodology. It's not really a major change in the methodology. It's sort of just making sure that we address the broader use case rather than strictly focusing on solar. So those are the use cases that we've been focused on in the work that we've been doing with Gridlab-d over the last 4 years. And so at this point, I guess I'm ready to sort of dive into the details of Gridlab-d and how it works. I'll pause for a second if any of you have any questions. Catch a drink of water while I'm at it. Okay, so if there are no questions, I'll move forward. Gridlab-d is what we call an agent-based simulator. And so what do we mean by agent-based? If you think about how traditional simulations work, typically you implement a solver for a set of differential equations, either ordinary differential equations, or if it's a dynamic transient solver in power systems, it might be differential algebraic equations. But regardless, you have a set of equations that describes the behavior of the system, and you simply take the information about the system and populate the parameters of the equation to solve those equations. Now, obviously, that is in itself quite a challenging problem. But what we mean by agent-based is the way in which we populate the equations, the solver's equations. In an agent-based system, we describe the different components of the system as objects, and each of them is modeled independently. And we use those objects' parameters, their properties, to develop all of the equations that will be used in the solver to solve the dynamics of the system and the performance, the behavior of the system, given the conditions that we observe in the system, including conditions that might come from other solvers. So for example, we might have a set of solvers that describes the buildings and another set of solvers that describes the power system. And together they create an environment from which the dynamic solution will emerge. So we don't solve the 2 sets of equations simultaneously because we actually can't. And instead we solve sort of alternating solutions in an attempt to get them to converge to some sort of agreed outcome. This has significant advantages and disadvantages. I'll talk about those in a minute. But basically, the reason we do this is that it allows us to create simulations that are more realistic in many ways. And they don't sort of presuppose the solution, right? You don't stipulate, oh, well, here's the Hamiltonian of my system, and now I'm going to write a simulator that implements the Hamiltonian, and I get a nice, perfect, clean solution. That's very useful for analytic purposes, but it's often not possible to even develop such a set of equations explicitly anyway. And it really gives us systems that look much more realistic in their behavior, in spite of some of the issues that might emerge from these. And so one of the things that we have to think about is how these simulations might not work the way we expect. So let me just kind of step back and give you what I would call a sort of a notional example of how this works out. So here's an example, sort of a canonical dynamic system that is often studied and is very helpful for understanding how these kinds of systems work. So a Lotka-Volterra model is a predator-prey model. You can think of it as foxes and rabbits. And so you have a population of prey and a population of predators, and the rate at which predators reproduce is a function of how much prey is available and how many predators there are, and the rate at which prey reproduce is a function of how many of them there are and how many predators there are. And so the dynamics of the system are fairly complex, but you can reduce them to a pair of differential equations that, as it happens, do actually have a solution. And the fixed point is really the point at which you would have a steady state. Now, obviously, the system itself doesn't. In reality, systems never sit at the steady state. For one thing, there are many disturbances that occur in these kinds of systems that prevent them from ever remaining at the steady state. But the other thing is they never actually can reach the steady state. They tend to deviate from it for a whole variety of reasons. So when you construct a simulation of a system like this, you find that depending on your initial conditions, it will orbit this fixed point that we have here at the solution. But if you think about the real world, nothing in the real world looks anything like any of these orbits. In reality, they do tend to look somewhat like this, but they move around in ways that look nothing like this simulation. And so the utility of the simulation is limited to sort of just getting an analytic understanding of how things behave, but not particularly useful if you want to, for example, create a training system for people who are going to be managing populations of animals. I don't know why you might want to do that, but to illustrate sort of the idea that if you wanted to use a simulation like this to create a training tool, that might not be the best approach. And so in an agent-based system, you might want something that looks a little bit more realistic. So one way you might do this is create a finite difference solution. And of course, the problem with finite difference solutions is that if you're not careful about how you implement them, they exhibit incorrect behavior, as this one illustrates. It's a naive finite difference solution that diverges. And that's also not realistic. It does have, you can see that it notionally has the similar behavior that we observe in the analytic solution, but obviously it's not going to work if you want to, for example, create a simulator for a training tool. In an agent-based environment, you explicitly model the predator and the prey, and you give each of them the kinds of rules that they might see in the real world. And what you see when you do this is behavior that is much more like what you would expect to see in the real world. In this case, the environment is relatively steady. And so what we see is that the population converges towards the fixed point. But if you run it near the fixed point for a long period of time, you'll notice that it never actually stays there. It tends to meander around that fixed point. in behavior that looks more realistic. And of course, if you were to disturb the environment in important ways, it would go back to sort of the larger scale convergent behavior, and perhaps it would converge to a new fixed point. And that's the kind of behavior that we were particularly interested in seeing in a tool like Gridlab-d. We wanted to create environments that looked realistic so that we could explore scenarios for smart grid technologies to see if we could prove that they don't work for certain situations and perhaps gain confidence that they will work for other situations. So this is notionally what's happening in Gridlab-d. We model everything explicitly, and then we try to solve for the behavior of each of the agents given the environment that they occupy. So how does this work? Well, fundamentally what's happening is that Gridlab-d has to answer, or every object in Gridlab-d has to answer two questions. It has to say, what is the state of the system at a particular moment in time? So think of it as the forward function of time, and identify any changes in those states given that time advances. And it has to answer the reverse question, how long before there is a state change going forward in time? And so you can imagine that the red line represents sort of the continuous time series for a particular object. And the dots represent the discrete time solution to that continuous system. And what we see is that there may be long periods of time when there's no change in state. And so what Gridlab-d takes advantage of is knowledge that the state has not changed and therefore no computation is needed. And instead, it simply answers the question, how long before there is a state change? And then given that state change, how long do we think it'll last? And if every object in Gridlab-d can answer that question and advance itself forward in time, given those answers to those two questions, then what we can do is develop a combined overlapping solution we call a quasi-steady time series solution to the system, where we advance the clock to the first object's state change, and then we let every object reevaluate whether the state change in one object might affect another object, and then ask that other object to reevaluate the answer to the question of whether its state change occurs at a particular time in the future. So this kind of back and forth between objects allows us to get much more detail, or reveal much more detail in individual objects without having to solve a simultaneous set of discrete or continuous equations that might be either cost prohibitive or flat out impossible to solve. And so this is what Gridlab-d does. This is how it works internally. You answer the forward question, what is the state given time step? And then at that time step, how long before you see the next state change? And then it knows how long to advance the clock by, and ultimately the simulator advances the clock by the maximum time it can, given what it knows about upcoming state changes in objects in the model. So that's the basic idea. Once you wrap your head around this idea of forward and back solutions, it seems like it's pretty straightforward. But as you know, or as you may know, there's this idea of conservation of difficulty. So there's a trade-off. And oftentimes, as we make the object models more detailed, the solution tends to approach essentially a finite difference solution, and the overhead of doing all of that work is sort of not worth it, and you might as well just switch to a finite difference solution, such as when we do with what we do with dynamic transients, where we know that essentially every time step, everything is affected, and it's not worth going through all the trouble of asking, and we simply switch to differential algebraic equations instead of ordinary differential equations. But fundamentally, Gridlab-d can manage this pretty well for reasonable sized models, typically on the order of hundreds to thousands of objects, this approach is extremely efficient and really gives you very useful results. So here's essentially what I mean by this forward and backward solution. So you can imagine that if I can calculate the state X as a function of time, then I may be able to calculate the inverse function, the time given the state. Of course, there are situations where this can be a problem. So imagine I have a system with or an object that has two basic behaviors, one that happens at a fairly long time scale and another that happens at a fairly short time scale. And so the question is, how do I solve for time in this case? It is possible to solve numerically, but it may be possible to use Gridlab-d's time stepping mechanism and simply approximate the solution, knowing that if we were to return an early time, that would be almost, control problem here, almost as good as answering the question accurately, because if Gridlab-d comes back a little bit early and says, I think I have a state change at the time, here, and it happens to be a little bit too early, it's just a little bit of extra overhead to converge to the correct answer, given that the time calculation was not perfectly accurate. And as long as it doesn't overshoot that, it's fine. And so this is a technique that can be used to approximate solutions when we suspect that it's not possible or not efficient to get a full detailed solution. But so far, what we find in many of our simulations, and this is true, for example, in residential buildings, is that implementing the full solution is just as good, just as fast, and it's not a problem to calculate these inverse solutions. So this kind of gives you an overview of how things work. There are some caveats. It is not unusual that we have to do iterations to find the next state. And because of that, it's certainly possible to implement non-causal behavior. In other words, the solution requires a condition A and not A simultaneously. For example, that would cause problems. Or the solution depends on information that is not yet available in reality, but because of the way the model is implemented, it's available instantaneously, and this causes sort of, how would you describe it? It's fundamentally non-causal in the sense that, or not strictly causal in the sense that the information that is being used in reality would not be available, and that delay might create a change in behavior. So the system is capable of dealing with many of those situations, but not all. And so it's not unusual to find in the development of a model that you create a situation that doesn't work, because in reality, that's not how things would actually turn out. So this means that there's really no guarantee of convergence. That lack of guarantee is always a potential pitfall in a Gridlab-d model. But generally, the implementers of modules and classes are aware of these issues and basically provide ways of ensuring that users don't fall into these little traps. So the mechanisms for that are pretty much in place, and we can deal with it. One of the other aspects of this that is an issue for Gridlab-d developers and in particular and advanced users is because of the layering of interactions that you find between objects, that you have, for example, houses and energy markets and power systems and generation controls, all interacting with each other in very rich and complex ways. When things don't turn out correctly, when you look at the answer and you look at it and say to yourself, well, that doesn't look right, and then you try to figure out why, it can be very difficult to diagnose. There are many interactions that are hidden. For example, in the power system, you'll have many current and voltage interactions that will span objects that occur, these interactions occur sort of at a distance, and it can be tricky to know which one is where the error is in the model. And that can make diagnosing and fixing model problems rather challenging. The other aspect of this is, of course, this can give rise to unexpected behaviors. But of course, that's the thing that makes this tool, that's the strength of this tool. You create a model, you run a simulation, and something unexpected occurs. That might actually be a key insight that you would not get from a tool that presupposes the answer or expresses the answer in a way that makes it impossible to reveal those sort of unexpected or unintended consequences from, let's say, a control strategy or a particular approach to modeling, constructing a network system, or a particular type of device interacting with another device. If you don't expect those behaviors and you model them in Gridlab-d, Gridlab-d may reveal them where other tools may never be able to reveal those unexpected behaviors. So that can be a very advantageous aspect, but it does create challenges particularly for novice users. Okay, so let me go over some basic concepts. Obviously, since we're dealing with sort of real world systems, power systems, there are certain things that dominate the behavior of the system in any particular case that you run into. Diurnal changes is probably the most significant one. The sun rises and sets, and temperature changes, solar gains change. These tend to be very strong drivers of how buildings in particular behave, and of course how humans behave over the course of the day. As you're at home, you go to work, you come home, you maybe go out, or you cook dinner, you sleep. Those things all reveal themselves in the system as behaviors that are highly relevant to how systems will function, and create that kind of variability that we're interested in seeing when we're studying, for example, how thermostats respond or how voltage regulators respond to changing conditions on the system. So these diurnal cycles are presented to the simulator through a variety of means: weather data, human scheduled behavior data, and such things. And so Gridlab-d has all the tools necessary to allow you to include that information, customize it, and we'll talk about schedules and climate and the climate module in the coming sessions. Obviously, it's not just the daily cycle that is important. Weekend, weekday changes also are significant, and some weather patterns that occur over periods of days also will emerge through the weather data files. So when we talk about schedules, we don't mean just the hourly schedule during the course of a day, but also the schedule during the course of a week. And as you'll see as we talk further, over the months, seasons, and years, these kinds of behaviors can be captured as well. And you'll find also that the weather data presents a lot of variability that is seasonal. That variability also shows up in the course of weeks. As you see weather patterns moving through a region, you'll see that in the data, the weather data, and you'll see the effect on the system itself. So as I said, seasonal cycles are also present in the data that's used by Gridlab-d. Daylight savings time is handled, although its contribution to outcomes is generally pretty minor. It's not, it does show up, and it can definitely be an issue when you're bringing data in from other sources, since not every source handles daylight savings times the same way. And we'll talk about that at some length as well. Tariffs, it affects the costs, and in some cases it can affect behavior. Time of use tariffs, real-time prices are designed to affect the behavior of people and the building control systems. And then, of course, just the general loading on the system, it can give rise to congestion on devices, as well as affecting the controls that govern how regulators and capacitors and switches and other such devices are affected on the system. So as a general rule, the kind of information that we need in a Gridlab-d simulation, or will get depending on the kind of problem you're studying, you will either provide this information or it will be provided by the simulator as a result of your simulation. But you should expect to either provide or get voltages on the nodes. You can get things like voltage drop over a line. The voltage controls on the devices themselves, regulators and transformers, low tap changers, and those kinds of devices. You can see the control positions. You can input those control positions if you need to study the response of other parts of the system to a particular scenario. Loads are very often needed. So if you're providing, if you're running a simulation where you want to provide the loads on the individual buildings, that is something that you can do from AMI data. You can generate load models from that data. You could generate loads from a physical model that is not reliant on data, but instead reliant on the building's design, right? What is its size? What kind of system does it have? How is it occupied? And all of that can give rise to feeder loads and power factor information that is useful in studying how, for example, voltage controls might be implemented more efficiently. Weather data is obviously crucial, as I said before. Very often we have to provide weather data in order to get realistic results. It is, although interesting, and it's not common, but it is interesting to provide a static weather input and do things like a step change in the weather in order to identify the model of a load or the model of a device's behavior in response to temperature changes. This can be particularly useful when you have to try to figure out why your model isn't working the way you expect it, and try to isolate which aspect of which object is giving rise to unexpected behavior. You can do the same with wind, with solar. These all affect the models in different ways. The weather data often includes precipitation, cloudiness, which can be very important for in understanding the impact of weather on solar PV, for example. Snowpack can affect ground reflectance that can increase heat gains, for example, in the winter in ways that might be helpful. And then, of course, we always get a lot of information about losses on the lines, on the service transformer to building line, the triplex lines that model the secondary part of the system. And then, of course, within the devices like transformers and regulators. Those losses are very important to track for certain kinds of studies that are being done, particularly studies where we're trying to minimize those losses, like volt var control and distribution level optimal power flow. And then finally, a lot of statistics can be developed from the data that is obtained from Gridlab-d. So you can provide energy prices. You can use those prices to get cost information and distributions of costs over long periods of time. You can also get information about duty cycles, changes in the duty cycles of devices like water heaters and air conditioners and heating systems, or even other appliances, which can be modeled explicitly if desired, although it's not very common that we model all the appliances in detail. And I'll explain later how we get around modeling all the appliances explicitly. We have implicit load models that allow us to avoid too much detail where it's not needed. So let me just kind of quickly go over some examples of studies that were done using Gridlab-d over the last 10 or 15 years. And I think this will help you understand the usefulness of the tool and the capabilities that it offers. So let me just first start with a really simple system to help understand kind of how things are done in Gridlab-d. So in this example, there's a single head node that in power systems parlance we would call the swing bus. It's the essentially the voltage source for the system, and we have a voltage regulator below it right here, and then another node that is host to two service transformers that serve two houses through triplex lines. And so these two houses are modeled explicitly, and their independent behavior will jointly affect the behavior, the loading that we see on this intermediate node 630, and of course the behavior of the regulator. And so when you run a simulation in a system like this, it's really quite surprising how much data you can get out of it. Essentially, in Gridlab-d, every property of every object can be measured. And if you look at a house, for example, a house has something, it has more than 100 properties that you can set, many of which will evolve over time in response to changing conditions. And of course, the nodes and the devices also have many properties of their own. And so you imagine if you were to run a simulation for a year and you're observing changes in these two houses that occur every few minutes or possibly every few seconds, and you were to collect all the data about all the changes, this would generate an enormous amount of data. So obviously, you need to be selective about what data you look at, but even the smallest systems can generate astonishing amounts of data. And in fact, for many of our test cases, this is essentially the kind of system that we look at. It has fairly well understood behavior. And so if we want to test a control strategy, or even test the house model itself, or verify that the voltage regulator works correctly, these are the kinds of scenarios that we use to validate individual behaviors of objects. Because if you think about how Gridlab-d is working, validating it against any other simulator is challenging because the other simulators don't work like this. And so they would obviously produce different results, which makes validating the system as a whole quite a bit more challenging. So it's these kinds of simple models that are crucial to a lot of the work that we do, or perhaps even simpler models where the result is static and we know exactly what we should get. If you think about how this model is put together, there's really two parts to it. There's the secondary distribution system itself, right? From you might think of this like the feeder, through the distribution system down to the service transformers. And then the residential portion of the model, in this case, from the service transformer down to the individual homes. If you look at, for example, simulations, models that come from other tools, generally the simulation stops somewhere short of the service transformer or at the service transformer. Loads are grouped together. This allows those simulations to focus on the secondary distribution system itself, and typically consider the rest of the simulation as sort of a boundary condition. But you can see that for the cases where you want to study the buildings in more detail, you have to go into that level of detail, and that results in a simulation that can take considerably longer to run, and of course will give you a lot more detail, a lot more data. So if you were to fully instrument a network like this, you might have to use recorders. These are devices, agents, objects in Gridlab-d that perform data collection for you. And so if you were to run, for example, at a 1 minute time scale, you'd get something like 500,000 power flow solutions over, say, maybe 50 recorders to get all of the data that is coming out of this simulation. Needless to say, that's an enormous amount of data to process, and you would get every time step solution, the power flow, and the individual building dynamics solved for every minute of that year. That's obviously not something we would typically do, particularly if you think about, the largest feeders that we model that might have, say, 2,000 homes on them. you probably would not do that. You would focus in on exactly the information that you need. And you might even break the simulation up into individual either weeks or months and simulate them separately in order to, and do them in parallel in order to improve the performance. When you do that, though, you have to be aware of the fact that the dynamics don't carry across from one state to another, and you would have to choose your initial conditions for the for each week or each month a little bit more carefully than you would in a year-long simulation, where the initialization transient might last only 2 or 3 days, and it doesn't really matter. In a week-long simulation, the initialization transient would take almost half of your simulation time. Probably not ideal. And even in a month-long simulation, the initialization transient might take 10% of your data. And so that would also probably not be ideal. So you have to be somewhat careful about how you set things up when you do this, but it is something that we do when we are trying to run very large-scale simulations over very long periods of time with very detailed models. So let me run through some examples. So here's a simple example of a demand response. And in this case, I'm trying to remember exactly what it is, but it looks to me like an HVAC demand response to a curtailment signal. And so this curtailment signal, I'm guessing it's a temperature set point change, but it's hard to know for sure. But what happens is that when the curtailment signal comes on, if you compare the base load in blue to the demand response, you can see that initially there's a pretty good response from the system, a drop of, at least a couple megawatts. But that eventually that demand response decays as the temperature set point, the buildings sort of settle into their new temperature set point and go back to their normal way of operating. And so that after a period of time, there really isn't much difference between the before signal, before time, and after the signal has decayed. And so what you see is that there's a transient response to the load control signal that eventually goes away. But when you release the control signal, there's another transient response that looks different. And that transient response persists for some time. And if you look closely, what you're seeing here is an oscillation. And for those of you who know how demand response, thermostatic set point change demand response works, what you're seeing is essentially a whole bunch of buildings behaving in concert with each other for a time before eventually that itself decays. So there's what's called synchronized states. And so this oscillation will persist for a time until that state synchronization in the thermostats dissipates. And in the meantime, what you see is that the load rebounded, right? There's more load than there would have been in the base load case. And so, yeah, essentially this is a kind of no free lunch principle. So first of all, the takeaways on this kind of a study are there's really no point in holding the curtailment signal. Well, there's no benefit to holding the curtailment signal during this time, except to the extent that you can defer when this kind of rebound behavior will occur. So in this case, the initial response is will be beneficial for peak load shedding, and then you basically hold the loads until you can absorb the rebound without adverse effect on the system. And so this sort of is instructive in helping understand how to design a direct load control strategy, understanding when you have to deploy it to manage the peak and when you have to release it to manage the rebound. And so this is just it's a good simple example of what you can expect to see from a Gridlab-d simulation. You get a very sort of realistic system behavior, and you get insights into what's going on, but not an analytic solution to it that you might get if you were to, for example, study transfer functions or something like that. Okay, so I mentioned earlier that there was a number of prototypical feeders. These were developed at PNNL about 10 to 15 years ago by Kevin Schneider, and these have turned out to be incredibly valuable resources for taking studies that you perform in one location and extrapolating them to other locations. So what these feeders do is they separate out regionally based on climate and sort of feeder design strategies. And so you'll see, for example, that in climate region 1, and by the way, I don't remember off the top of my head which one is climate 1, 2, 3, 4, and 5. That I'd have to refer you to Kevin's paper. But you'll see that in climate region 1, there are a variety of feeder types that address different kinds of distribution systems, different customer mixes, different voltage levels, and different power capabilities, different overall loading. And so there, these voltage levels essentially address the sort of the typical designs that you find in that region. Some regions have higher voltage systems because they tend to have higher population concentrations and different kinds of loading conditions than in other parts of the country. The other thing that's important about, these feeders is that if you look at Kevin's paper, we know sort of what the representative fraction of each feeder is relative to the total population of feeders in the United States. And so that allows us to do these sort of regional to national projections and take a study and extrapolate at a national level to some extent. Obviously, it's not perfect. For one thing, there are no dense urban feeders here. These are all radial systems, and in dense urban systems, they tend to not look like that. But for another thing is, over time, we should expect that this mix, the weighting of this mix might evolve. It's been 15 years since the work was done. We would expect that to evolve a little bit. Perhaps it might be, there might be some advantage in doing a study to update this at some point in the future. But this remains an extremely valuable resource for anyone who's working with Gridlab-d models and trying to study a particular problem and are interested in extrapolating at a national scale what the implications of the results that they have might be. So here's an example of one such study. Again, Kevin conducted this study. It's an integrated volt var control. For those of you not familiar, on power systems, we have to control the voltage in order to keep up with changing loading conditions. And so if you think about, for example, the IEEE 13 bus system, which is shown here, there's a voltage regulator that has to be controlled. And as the loading conditions change on the system at each of these networks, that voltage regulator would be expected to move up and down. Now, what integrated volt var control does is it not only tries to regulate the voltage so that you keep up with the power, but it also is designed to regulate the VARs to try to minimize losses. And these strategies are more complex to implement. And there's probably, well, my guess is there are many strategies. There are vendors who sell strategies, but there is one that Kevin studied, which was openly available from a paper that was published now more than 20 years ago. And so he used this control strategy in Gridlab-d to examine how things might look different and what the implications at a national scale would be to extending it if we were to use it on every feeder in the taxonomy feeder, and what that might look like at a national level. So, so you can imagine, for example, we have a system that has voltage regulators and capacitors, and you can see that the voltages on the lines on each of the phases change over the course of a day. Not at all surprising. This is what the tool is supposed to do. This is what you tend to see in reality. And of course, if you just operate voltage control, the power factor is not necessarily maintained very well. I mean, it's not terrible, but it's, it's not ideal. And so you can calculate the total power and energy consumed on the system. And so the results of running the simulation with just voltage control gives you a certain sort of total power and real power delivered. And you can see that the VARs are not insignificant, not terrible, but there's considerable amount of VARs that are being used on the system. If you enable volt VAR control, then the voltage is controlled differently, and the result of that is that we see a significant reduction in the VARs consumed by the system, and as a result, the total energy required to deliver the real power to the customers. And what you see in the power factor is that there's a much better tracking of the power factor during the course of the day. Not perfect, because the control strategy still has to deal with significant changes and their limitations in how fast it can act, but the overall result is significantly improved. So this idea of volt-VAR control can be studied on all of the taxonomy feeders, and then we can extrapolate at the national level what the implications are. And so here's a sort of examination of the change that you see as a result of applying volt-VAR control on each of the taxonomy feeders. And what we see is that there's generally a reduction in the peak demand, but not universally. You notice that there's one feeder here that has a pretty significant increase in the peak demand. And the reason this occurs is because the nature of the loads and the design of the system are such that volt-VAR control, actually lowering the voltage, actually increases the load on peak, rather than decreasing it as you might expect if you had, say, lots of constant impedance loads and not many constant power loads, or loads that respond in a manner that, how do I put this? Basically, they look like the load increases with voltage. So think about, for example, if I have a thermostatic load and I decrease the voltage, you might expect the thermostatic load to run longer, right? And that might result in a behavior that's unexpected. So you can see, depending on the nature of the load, there may be increases if you exercise volt-VAR control. In other words, you raise the voltage or lower the voltage. So, and you can see that the percent change on the peak demand is pretty significant. It's not, it's not a trivial amount. So the takeaway is obviously that volt-VAR control is not a universal fix. And in other cases, it simply doesn't do anything at all, or hardly anything at all. And so it's not, it's not always going to be a solution that you would apply everywhere. And if you look at the energy, it's a similar story, right? You don't always see an energy benefit. In some cases, you see an energy cost associated with deploying it. And so the main takeaway from this study was that if you wanted to deploy volt-VAR control, you might deploy it on, say, only 40% of the feeders, and you would get about 80% of the result. It's not a universal beneficial thing to do. And I think this was, an important insight. This paper, became sort of the first major contribution that Gridlab-d offered to understanding how smart grid strategies needed to be thoughtfully deployed. So at this point, I want to offer a quick break for anybody who needs one, and we will return in 5 minutes. I'll stop recording at this point, and if you have any questions, now would be a great time to post them in the chat, and I can return. And when we return, I'll try to answer them. So let me pause. All right, welcome back, everyone. So the next part that I will cover, we're going to start talking about Gridlab-d in a little bit more detail, and talk about the modeling language for the rest of this session. And And then in the next session, we'll get into the installation and setup process for developers and for power users. So I'll try to hold enough time for some questions at the end, but I'm running a little bit behind schedule, so I'll try to pick up the pace a little bit as well. All right, so let me just jump right in. So Gridlab-d uses what's called a GLM file, which is a Gridlab-d modeling language. It's a file that basically represents all the objects, classes, players, elements of a simulation. And in the case of HiPAS, not only does it accept the GLM files that the original DOE version of Gridlab-d accepts, it also accepts a number of other file formats, which it will automatically convert to Gridlab-d GLM files and any other files that might be needed in order to fully address the conversion of the source data. So for example, if you have a SIME model, it might create multiple GLM files, or if you have some AMI data, it might create a GLM file and a CSV file that links the data that's in the original AMI data set to the Gridlab-d model. So these automatic conversions generally result in a GLM file, as well as other files that allow you to hook up everything and connect all the various components together more easily. The great thing about GLM files is they're relatively easy to read and to edit. They have this really extensive syntax that allows you to construct a model fairly quickly and easily, and allows you to attach together multiple models and link the different components together. Sometimes you can even use a single object definition to define an entire population of objects, and properties of objects can have statistical distributions, and so on. So there's a lot of richness in the language, but because Gridlab-d is so different, the language serves Gridlab-d's modeling requirements pretty well, but it also means that it's not really directly compatible with any other software tool that's out there. If you think about, sort of the Venn diagram of what GLM represents versus what a SIME model represents, it's not a perfect intersection. There are things that you can represent better in SIME that are difficult to represent in Gridlab-d, and vice versa. It's not unexpected, but it can be a challenge for those who are trying to work with both tools and move data back and forth, because the kinds of analysis that you're trying to do requires different tools. So what do you find in a GLM file? Typically, you'll find class declarations, object declarations, modules, the various things that you need to define objects in different domains, like in power flow domain or in buildings or in markets. You can modify classes and add new classes very easily at runtime. You don't have to build a new module to create a new class of object and link those objects to existing ones or to give them new behaviors. And overall, this is what you use to essentially construct your model, define the initial conditions, set the boundary conditions, and set the clock so that you can start time and stop time as desired. And then, of course, you can add other objects that will move data in to help you change the boundary condition or pull data out to record how conditions or properties of objects change. So as I said, classes can be defined in modules. So modules basically collect a whole bunch of classes that have some kind of interrelated or internal, maybe background behavior that connects them together. So for example, a power flow module would have a number of classes that implement nodes and links and things that are a node-like nature and things that are a link-like nature, and up to the point where you're defining the individual objects like a switch or a transformer or a power line. And those objects essentially represent or contain all the properties that are needed to solve the power flow solution. And it's the power flow module that actually develops the power flow solver and solves it repeatedly over time as conditions change. So the modules are loaded on demand. You basically say, I want the PowerFlow module. You might set some parameters for the module that define and control its behavior. For example, the PowerFlow module, you can set a parameter that allows you to choose which solver you're using, whether you're going to use a Kirsting's forward backsweep method or a Newton-Raphson solver. Solvers can be proprietary. I'm not aware of any proprietary solvers out there. I think all of the solvers that are available are open source. And most of the solvers developed by P&L are included in HiPAS, but not all. Some of them were not ported over either because they didn't really support the use cases, or they were still too early in development at the time we started the work on HiPAS, and they'll be brought over at some point in the future. So let me just quickly go over the modules that are available. There's really two categories of modules. You have modules that are used to model systems, and modules that provide what we call utility functions or supporting functions. So the first category is system modeling. We obviously have things related to climate. So there's a module that deals with weather data and typical meteorological year data from NREL, so climate data. There's a commercial buildings module that implements buildings that, essentially it implements all buildings that require three-phase service. A connection module that allows you to connect to external things like devices, hardware devices, and so on. This is particularly useful if you're doing hardware in the loop simulation, and you need to get Gridlab-d to communicate directly with those devices, sort of in an outbound direction, especially, but it supports both directions. Generators, which implements basically various energy sources at the distribution level. So inverters, photovoltaic and battery inverters, diesel generators, things like that. Industrial load that basically implements a variety of industrial systems. Think of them as NIAX code-based load shapes, essentially. Markets, and especially distribution level kind of markets like you would see in a transactive system, particularly traditional transactive systems, as demonstrated in a number of projects at PNNL over the years. PowerFlow solver, which I've mentioned already, which solves the PowerFlow problem for distribution systems. A reliability module, which implements the IEEE 1366 reliability metrics. A resilience module, which implements essentially the DOE GRIP project, which is the Grid Resilience Intelligence Platform, mostly focused right now on pole resilience, pole infrastructure, vulnerabilities, and the influence, what's coming also, which is the influence of vegetation on resilience. A revenue module, which focuses on billing systems. A tariff design module, which focuses on modeling different tariffs. And a transactive module, which is sort of the more advanced transactive features coming out of current DOE projects. And then on the simulation utility side, we have an assert module, which is used to verify that certain properties meet requirements during the simulation. So for example, you could assert that the voltage is within a certain band on a particular node, and if it isn't, it stops the simulation. This allows you to catch the simulator doing wrong things, or ensure that the simulator doesn't do something wrong as your simulation moves forward in time. Two database, InfluxDB and MySQL databases. Different kinds of databases that have different characteristics. MySQL is a very common database, relational database system, and InfluxDB is really good for time series data collection. An optimization module that does fairly crude optimization, basically a simple gradient search optimization, but it's integrated into the solver, which means that it allows you to optimize across the properties of many objects, which is a very potentially useful capability. Although, as many of you know, these kinds of mixed discrete optimizations can be extremely time consuming to solve. And then a tape module, which allows you to play data into a simulator or record data out of a simulator. Yeah, tape is a nice anachronism, since that refers to something that many of us have not seen in many years, and some of us have never seen. Tape players, tape recorders. Okay, so those are the modules. Now, within modules, we have these classes. The purpose of a class is define objects that have similar characteristics, and those characteristics are both properties of those objects. You know, so you imagine, for example, a house, it might have a square footage associated with it. Different houses have different square footages, but all houses have square footage. And then some behaviors. So those houses might have different kinds of heating and cooling systems that behave differently. That can be set by the parameters, the properties of the house. And so one house may have only a gas heating system, and another house may have a heat pump, and those would behave differently, but they're both houses. They're both the same class. They just have parameters that affect how they behave differently. And then some objects expose methods that can be used to provide information to the objects while the simulation is running, or extract information from objects in sort of non-typical ways, not the way a recorder would work, but other kinds of dynamically changing information. Now, in the case of modules, these classes are pre-compiled, so they're pretty static, but because they're compiled, they're written in C++ and they're compiled in, it's not unusual for them to be extremely complex and rich. They have a lot of detail in them. There are many ways people use them, and so they have lots of options that you can use to turn different things on and off. And so they can model a lot of different things, but they can also be very challenging to use in certain situations. You may have to spend considerable amount of time going through the documentation to figure out which parameter controls the particular feature that you're interested in. The other way of creating a class is to create what's called a runtime class. And these are essentially classes that are built when the GLM file is loaded, based on what's provided in the GLM file. So those are a lot easier to put together. As a result, you can really focus on the thing that you care about and not have to deal with all the stuff that's not important. But if you need to make them very detailed and very efficient, that can be a bit more challenging. So there are two ways of implementing them. You can implement runtime classes in C or in Python. But at this point, in HiPAS Gridlab-d, doing them in Python has generally been found to be much easier. The C implementations do work. They're very fast, but they tend to be a little bit harder to implement, and they do require considerably more programming skill than Python does. And so as a general recommendation, Python runtime classes are better. They're easier to deal with. Okay, so when we put together a GLM model, we have to define objects. Each object at a minimum describes a single instance of a class, but it could be used to describe multiple instances with potentially distributions of properties, so that you can say, for example, I want 10 houses, and I want the square footage of these houses to be normally distributed around 2,000 square feet with a standard deviation of 100 square feet, for example. And so it's quite easy to implement objects in a model that have a range of properties that you can use to study sensitivity, for example, to those properties. One thing that's very important to understand in Gridlab-d is there is what's called a parent-child relationship. And that parent-child relationship dictates how the solvers work. So it's not used in any other manner. It's really just to help the solvers know which objects have to be solved before which other objects. And so we have essentially what's called the top-down and bottom-up solution method, where a top-down method starts with the parent and works its way down through the object hierarchy, solving so that the child can get its dependency on the parents first before it does something. And then a bottom-up method where the child can update its values so that the parent can then do its gathering operation and collect information. The way Gridlab-d works, the child object is expected to get and put information to and from the parent. Parents are largely ignorant and unable to get lists of the objects that are child to it. And so those objects typically have to wait for all the child objects to update. And that sort of dictates a lot about how solutions get implemented. All right, so here's a simple example of defining a house where we accept essentially all the default values that Gridlab-d will generate. So in this case, we declare the residential module, and then we declare that we want to create a house, and we give it a name. And that's sort of the minimum. In fact, you don't even have to give it a name. If you don't give it a name, Gridlab-d will automatically give it a name that follows a convention of basically class, colon, and then a number that represents the object's ID number. But this is the minimum definition really that is necessary. Now, you can also then set values of the properties of different houses. So here's a little bit of an extended example where I first load weather data, and then with the weather data, I define the house. And the reason I bring this up is because in this particular example, we would find that given the size of the house and the heating set point, the Gridlab-d house creation process will look at the weather data for Los Angeles and design a house that adequately meets the requirements for that climate. So the size of the HVAC system, the insulation, the quality of construction will be sort of based on the weather data there. So a lot of the settings that are done automatically when you don't specify them are going to be a function of climate. So you have to be aware of that. And even when you don't provide this, there's still a certain amount of randomization that occurs in each house. So if I were to define multiple houses, they would not be identical. They would have some differences because there are some properties which are never set identically from one to another. And so that randomization process is inherent in how a lot of objects get created, particularly things like buildings and so on. Probably the next most important thing is the clock. As I said early on, Gridlab-d models a time series, what's called a quasi-steady state time series. And so we have to say when we want the clock to start and when we want the clock to end. And the simulation will advance through from the start time to the end time. The clock can represent times going all the way back to 1970, but the default start time is 2000. And I believe the latest time it can represent is 2999. So hopefully I won't be around then. Yeah, so it can simulate quite a long period of time. And as a default, though, it generally will start at 2000, and it will run until the simulator reaches steady state. And there's a special value that's used to indicate that steady state is the desired stopping condition. Otherwise, if you provide a time, it will stop at that appointed time. Just so, FYI, all objects have an internal clock as well to help them know whether they are up to date relative to the system clock. And as a general rule, those two clocks should be the same. If they're not, that means you're in the middle of a synchronization event, which is okay. But you can use that difference sometimes to help you know just how big this event is, although generally solvers know that anyway. They know how big the time step is. but sometimes you do need to consult the object's local clock in order to know what to do. That's pretty unusual though. The other thing to know about the clock is that it's all based on the local time zone. So a particular distribution system runs in a time zone. The simplest way of describing a time zone is to give the POSIX standard, what is the standard time, what's the offset from Greenwich Mean Time, and then whether there is summertime implemented as well. You can provide the time zone information by giving a location, and there's a couple different ways of doing it. You can do it sort of this localization method, which is country, region, city. You can also use the ISO standard, which I think is something like America's Los Angeles. It's one that you find fairly commonly in Linux systems when you set them up. All of these are supported. They change over time, so we try to keep up with them. But generally, at least for North America, everything is implemented. And for most of the world, they're defined as well. One very important thing to understand is the way daylight savings times rules are implemented. Unlike tools like Excel, in fact, most tools on systems, the daylight savings times rules change from year to year. So if you run a simulation, for example, before 2006, you will see the daylight savings times rules that were in effect at the time. If you run it after 2006, as you may know, there was a change in the daylight savings times rules in North America. The new daylight savings times rules would be in effect. And in fact, if you were to run the simulation spanning that, you would see them change as time went by. And so that's an unusual thing in Gridlab-d and something to keep in mind. Right now, for example, there's some discussion about whether to abandon daylight savings time or to change it again. And we can certainly deal with that question very easily in the file that describes daylight savings time. And in fact, we can test to see what the effect might be, if any. So here's a clock definition. This is almost always how it will look. You'll specify the time zone, you'll specify the start time and the end time of the simulation. And as I said, if you specify never as the time, then the stop time is simply the next steady state, which may or may not ever occur. If the simulation never reaches steady state, it will literally run until the clock runs out, which is at 2,999. But that's hard to do, actually. It can be done, but it's not that easy to do. So here's an example of a clock definition in conjunction with the house definition that we saw earlier. And so what this would do is, if you were to just run the house simulation without a clock, it would solve a single instance, a moment in time, and then nothing else would happen and the simulation would exit. Now with this clock specified, it's going to run the house from January 1st, 2000 to July 1st, 2000. So you get a 6-month simulation of that house. Not much you're not going to see much. It'll just say, yeah, I did it. And the reason you won't see much is because you didn't do anything to collect data. So you don't know what it did, but it did something. And so how you run a simulation, at the command line, you just specify the tool Gridlab-d and the name of your file. And then the output goes to your current working folder unless you specify otherwise. And so, for example, you could tell it to run the simulation and then send the output to a JSON file. Or you could send it to another GLM file, but please don't send it to the same GLM file, and you will overwrite your results, your input, and that input will, it'll now be your output. Yeah, I think we all make this mistake at least once. Some of us make it more than once, myself included. It's actually remarkably easy to do. So that's basically how you run a simulation. It's not too difficult. Do keep in mind, you can chain together multiple GLM files and it will load them in the order in which it finds them. And as I said, you can put other types of files, and if the conversion is obvious, it will do them. And if it's not obvious, you'll have to provide additional information to tell it how to convert it to a GLM file. And we'll talk about that when we get to the converters section. Okay, so as the simulation runs, you can get a lot of different output messages to the console. Informational messages are not generally important. There aren't that many, actually. The tool does generate a few of them, but there's not that much. Verbose can be very useful for diagnosing relatively straightforward problems. Something doesn't quite happen the way you expected. If you turn verbose on, it outputs more information about what it's doing, and that might help you isolate your problem. If that doesn't cut it, you can turn on debug. Debug is extremely chatty, and it will give you a lot of detail about what the different parts of the system are doing and what they're communicating to each other. And so you'll see things like object such and such advances the clock to this time, and this object doesn't need to advance the clock. This object goes to this state. So there's a lot of information that can help you diagnose more serious problems about what's going on. The system by default is set up to issue warnings when it encounters them. Warnings are considered problems, but that might affect the correctness of the result, but not necessarily. It doesn't know for sure. And so they're generally not considered serious problems. Nothing that would justify stopping the simulation. Errors are serious problems. When you get an error, that means the result is compromised, probably the result can't even be achieved, and the simulation's going to stop. It might not stop right away. It might take it a few, let's say, extra steps to unwind whatever it is doing, and so you might get multiple error messages in a row. My advice would be to pay attention mostly to the first error message, because that's probably the one that initiated the cascade of errors. The other errors might be helpful to help you see how it got to that final error, so you can see which part of the system was contributing to it. And oftentimes, warnings eventually lead to errors, and so looking at the warnings is quite useful when you see an error. Usually fatal is the last thing it'll tell you right before it dies. And that's basically, it's telling you that the halting condition has finally been reached after a sequence of one or more errors. Sometimes you might get a fatal error without an error warning, but that's pretty unusual. Basically, all fatal is telling you is this is how I ended it. And then exceptions are reserved for things that were completely unexpected, and that the core engine or the module or the tool simply could not handle. And usually those are instantaneously fatal. The simulation will exit immediately. It might save a dump and it might not. Depending on where the exception occurs, it may not be able to save an interim result. But generally, when errors occur, even exceptions, generally it will be able to save an intermediate result of the model so that you can kind of see where things are at. Maybe the result is enough to get you what you want, and likely that result will be helpful in diagnosing the cause of the problem. So, so the way you control these, you can disable warnings by including the warn flag on the command line. Note one thing that's important to note about these is that they are immediately implemented at the point in which they're encountered during the processing of the command line. So, for example, I can disable warnings, load the file, which means that any warning errors that come out of loading would not be displayed. And then I can add another -- warn afterwards to re-enable warning after that file is loaded, meaning when the simulation starts and runs. So this kind of feature allows you to control which mode is used at which stage of the process of loading, initializing, and running the simulation. Verbose obviously affects whether the verbose mode is turned on. Same thing with debug. And then quiet essentially suppresses just about all the messages that would come out of the simulator, I believe, with the exception of exceptions. I don't think quiet suppresses exceptions. Okay. So at this point, we've talked mostly about modules and sort of the components of your simulation system. There are a lot of parameters that govern how Gridlab-d functions overall, or how a module functions overall. Those are called globals. To set a global at a command line, it's simply a matter of using the -d option. The name of the global equals the value that you want. And that global will take effect immediately in the processing of the command line, again, so that you can change how that global is set as you process different GLM files. And you can essentially manage these settings during the loading of both the overall model as well as settings that affect the behavior of individual modules. So for example, if I want to affect a power flow module global, I would simply use power flow : whatever the name of that module is. We'll talk a lot more about globals and module globals and so on when we get into the GLM language itself, but that's a few sessions away. And there's a lot of stuff to talk about, but this is sort of the command line level control over those. So here are some examples of globals that are useful. I mentioned early on, iteration, you might have convergence issues. Gridlab-d has an iteration limit of 100 iterations before it will consider convergence having failed. It's pretty rare that you have a model that requires even 10 iterations, let alone 100. But it can happen. And so if you run into situations where you're hitting the iteration limit, you can increase it if you need. We've talked about random number generators. Every object has its own random number generator, which is seeded. The seed is determined by an entropy source on your system, so every run will be different. If you want to disable that, you can either set the random number seed to some specific number and cause it to essentially follow a deterministic sequence of random numbers, so that given that seed, the simulation will always repeat the same random number sequence, and essentially you get the same result every time. Unlike what would happen if you were to not set the random number seed generator and let it remain 0, then you get a non-deterministic sequence of, well, I shouldn't say it's non-deterministic. It's a pseudo-random source. The entropy source on your system is pretty good, but it's not strictly non-deterministic. Let's see, minimum time step allows you to control we talked about the time stepping in the mechanism. It allows you to control the smallest time step it's allowed to take. Apologies for the typo. This is time with an E. The default is 1 second, but you can increase it to 10 seconds or a minute or even an hour if you want, depending on the type of objects that you're dealing with and their dynamics. You can essentially exclude certain dynamics from your simulation. And that can have very beneficial performance effects. The maximum sync time controls how long any given object is allowed to solve its next state. The default is quite long, it's 60 seconds. And the reason for this is that there's one object in the power flow module which might need considerable time to solve, and that's the swing bus. The swing bus is responsible for solving the power flow, and so it needs more time than most other objects. If an object takes more than 60 seconds, it's probably stuck in an infinite loop. This will stop the system when that occurs. The maximum runtime is essentially the maximum time you will allow the simulation to run total. By default, it's 0, which means there's no limit. But if you're running a very large set of jobs and you're not certain that all of the simulations will run in a reasonable amount of time, or you don't want it to consume all of your resources on AWS, for example, setting a maximum runtime is probably a wise thing to do. You can always come back and figure out why that particular, if you're doing a batch of, say, 1,000 or so simulations, why that one in particular ran too long. But this would avoid you having, runaway jobs. And then finally, save file. This is essentially the file that when the simulation is done, we'll receive a dump of the final state of the system. And so that way you have initial and final state both saved, which is generally pretty useful. Okay, now reading error messages. When you load a module, it's pretty common to get messages that come out, either warning or error messages. You'll generally see that message come out in the form of the name of the file, the line number in which the message occurred, and then whatever the message happens to be. The same is true for runtime compiled files, except that it might have a CPP instead of a GLM. And whatever it is the message is would be coming from the compiler, not from Gridlab-d. So that would be generally a language issue rather than a modeling issue. Once the simulation starts, you can get messages from the simulator. Now, generally messages are in the form of a tag, which indicates whether it's a warning, verbose, debug, error, fatal, exception, etc. And then the timestamp, the time on the internal clock at which that error occurred, and then whatever the error message is. If you get an error from a tool or a subcommand or a converter, it will have a similar format, but instead of a timestamp, it'll have the name of the tool, command, or converter that caused that error, and then of course the error message. It is fairly usual, it's not universally true, but it's quite common, that if you have the debug flag set on, the error from a tool like Python will be followed by a traceback, which for those of you who work with Python is really useful for identifying the source of the error. And what it means is that if you're, if you're having troubles identifying the source, if you turn on the debug option and run it again, you should be able to identify where the error came from. So that's generally how you read outputs from loading and running simulations. So at this point, what I'm going to do is just wrap it up, give you some sources where you can get additional information, and of course your homework assignment, because as you know, you can't have a course without homework. Your homework assignment for next week. So to get the source code from Gridlab-d, it's on GitHub. It's source.gridlabd.us. The announcements page is news.gridlabd.us. If you want to report any bugs, issues, questions, it's issues.gridlabd.us. So code submissions, for those of you who get to that point, those are found at polls.gridlabd.us. For those of you who are not familiar with GitHub, a pull request is how you submit code. If you want to write an email to the administrators, developers for the Slack Gridlab-d team, it's gridlabd@gmail.com. And it works. It's not always the quickest way of getting a hold of somebody because honestly, I need to look at it more often. I'm not in the habit of looking at it every day. It does forward to my inbox, but I don't always catch them. The other thing I don't like about email is that if it's a good general question, which most of them are, if I answer the email directly, other people don't benefit from it. And quite frankly, I think it's better to use the discussions pages on GitHub for asking issues and discussions pages for asking questions and getting answers. I think that's better for the community as a whole. But otherwise, feel if it's a private conversation, something you don't want to talk about publicly, then this is absolutely the way to go. The email is fine. When you're running Gridlab-d, there are actually some online, directly from Gridlab-d help mechanisms that you can use. So there's the help itself and what's called mod help, which gives you help about a module or a class within a module. Those are quite useful. There's actually another one I forgot to mention, which is info. If you type in --info equals and then some topic, it will look up. Oh, I'm sorry, it's down here. If you give type in info topic, it will look up on GitHub where that anything related to that topic. So it searches GitHub documentation for that. You do need to be logged in on GitHub for that to work. It does not work if you don't have a GitHub token. And then lastly, the general documentation is available at docs.gridlab-d.us. And what's particularly useful about this documentation is that it's published by branch. So as developers work on different branches, the documentation is modified. And so you can consult the documentation for that branch and see the differences between different branches directly. You're not always reading the latest documentation, you're reading the documentation that's for the version that you're interested in. Okay, so yeah, here's how the help works. It just displays each of the command line options. There are many. This goes on for several pages, so I'm not going to show it all, but you get the idea. It tells you what the option is and what the what it means. If you want mod help player, for example, tape player, it displays the module globals that are relevant to that module and the properties for that particular object. Here's a much more detailed one. Power flow lines are much richer, and so you can see that it's got a class definition structure, a parent class power flow object. It's got some methods and so on, and you can see the properties listed. You can get an example of an object. Basically, it creates one for you as a template. It's not necessarily going to be a working example. You can see here that the clock is not valid. It doesn't have anything to work with, but it gives you a starting point for an object if you want that. And so general developer resources, this is what the documentation looks like. You have to select the project, which is always Gridlab-d, the branch that you want to look at, and then you can look up the topic in here. If you're logged in on GitHub, you can search the topic and find anything that you need in the documentation. The source code is on GitHub. So when you go to source.gridlab-d.us, it just redirects you to GitHub itself. And so you can see the branch, all the branches that are available. You can look at the issues, the pull requests. You can participate in the discussions. Actions basically are things that are done as a result of polls when people submit code. And of course, you can look at the wiki, which is for developers. Docker Hub is one of the distribution mechanisms. Those who are not familiar with it, it's how we distribute images that run in Docker. And the same thing is true for Amazon AWS. And so there are a number of AWS Amazon images, and they will be maintained and updated as we create new versions. And so finally, the homework assignment for next week is to read the wiki pages on GitHub and follow the developer instructions for whatever platform you're using. And yeah, we'll report back next week on who tried which platform and what happened. In a sense, you're kind of a guinea pig. We're validating the distribution infrastructure this summer, and I'm interested to see how things go. And if you have any questions, feel free to reach out to me or Alona, who is also on the line. And we can probably help you out with whatever it is that you run into. We're here for that. And I think that's it. I'm sorry I only left 1 minute for questions, but I'm happy to hang a little bit here while if anybody has any questions. So with that, thank you very much. And I am interested in your feedback and how this is organized. If this works well, if there are things that we can do better, please let me know. I'm assuming you all have my email because it should have been in the invite. Yes, I will provide a copy of the slides and make those available. They'll actually be put onto the GitHub documentation for the user tutorials. Okay.
Thank you, David, for the presentation. Really appreciate that. And this is Yahoo Yang with CC. I just have a quick question regarding the inputs for the simulations. So for the buildings, actually, do you need also to consider the orientation of the building? For example, the number of windows, so that that may actually affect the general annual energy consumption?
Yes, if you're defining a physics-based model of a building, you can specify the orientation of the building and the window to wall ratios. So those are options that you can specify. They're not generally as detailed as you might find, say, in PowerDoe or tools like that. I'm sorry, I dated myself. PowerDoe is the older version, but you know what I mean. These models are reduced to some extent. So the orientation does affect how the solar gains are absorbed by the building's mass, but yeah, it's not quite as detailed as you might imagine. We could go into more detail. Comes at the price of speed, though.
Yeah, yeah, understood. Thank you.
Yeah. Any other questions? All right. Well, thank you, everybody. And I wish you all a good day, and we'll get together next week where we will go over installing and building Gridlab-d from the source code. Thank you, everybody.
Have a great day.